started with chapter 11. Remember, I told most of you last week, if you didn't hear it, that this is our last unit and it combines 11 and 12. 11.1 is pretty short. I think 11.2 is super long. And then we just have 12.1. So if you didn't get a copy of the notes, which you probably don't have any if you're at home, just don't copy the whole thing. There we go. That's what I was hoping for. All right, so 11.1 chi-square test for goodness of fit. Someone called chi-squares. I just say chi. It's whatever you want to. I don't care. All right. So computing expected counts. Jerome's class collected data from a random sample of 60 M&Ms. So they were looking at M&Ms packages and talking about the expected counts for each color and what they were saying. So 60 M&Ms, milk chocolate candies, calculate the expected counts for each color. So here's your hypothesis. Okay. The probability of getting blue was 0.24, and this is within the problem. I just didn't copy that whole problem down. Your probability of orange was 0.20. Yellow was 0.14. Red was 0.13. Brown was 0.13. And then green was 0.16. All right, so that's what it was said that in the candies, that's how it was proportioned. So Jerome's class collected a random sample of 60 M&Ms, calculate the expected counts for each color. So what are the expected counts? All you're gonna do for expected counts is the sample size times the proportion, which is exactly what I gave you up here. So you have all that information now that I gave you this. So blue, we took it out of 60 candies. If there are 60 candies and there's a 24% chance of getting blue, that would mean that your sample of 60 contained 14.40 blue. So I would say somewhere between 14 and 15. To get orange, you would do 60 times your orange percentage was 0.20, which gives you 12 orange. And I don't have to put that on there. You don't have to rewrite that. Okay. I'm going to do red and brown together because they were both 0.13. That's what I was about to say. It's perfectly fine doing it like that as long as you label it. 0.13, which would give us 7.8 of each of those. Yellow, you would do 60 times 0.14, which would give you 8.40. And then the last one would be green, which you would do 60 times 0.16, which gives you 9.60. In a COVID-free world, we would have done this together. I would have brought M&Ms in and we would have done it together. Okay. Any questions on the first one? That's literally all you do. Okay, expected counts. The next page, chi-squares statistic. I don't know why I have such a hard time with that word. The chi-square is a measure of how far the observed count are from the expected counts. The formula for this statistic is, it's like, that was terrible. It's like a curly X. Okay, it's like a curly X squared. It is the summation of the observed minus the expected squared over the expected, where the sum is over all possible values of the categorical variable. So then in the next one, we're going to do that. We're going to go back to that M&M's chocolate candy. The table shows the observed and expected counts for the random sample of 60 candies in Jerome's class. And we're going to calculate the statistic. And we are going to do this one by hand. Okay. So that chi-squared, you're going to do your observed minus your expected. So for the blue, observed minus expected squared over the expected. And then you're going to add the next one. Your observed minus your expected squared over your expected. Observed minus expected squared over your expected. I'm going to continue to the next line so you guys can see it. 15 minus 8.40 squared over 8.40. 10 minus 7.8 squared over 7.8. And 6, excuse me, minus 7.8 squared over 7.8. When you put that all in your calculator, you get a value of 10.180. Any questions on how to find that? Observed minus expected squared over the expected, and then add them all up. Mars Incorporated reports that their M&M's peanut chocolate candies are produced according to the following color distribution. So there's your percentages that I kind of gave you in the very beginning. These are different ones though. Joey bought a randomly selected bag of peanut M&Ms and counted the colors of the candies in his sample. He had 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown. State appropriate hypotheses for testing the company's claim about their color distribution of M&M's peanut chocolate candies. So here's what they're saying. Sorry, this should be number 1. Your null hypothesis is that the company's distribution claim is correct or true. So these are the ones we're trying to vote against, okay? So that's your null. Your alternative is that the company's distribution claim is not correct. And that's it. That's your number one. Calculate the expected count for each color, assuming that the company's claim is true, and show your work. So let's start with blue. Start with blue. What are we going to do? How do we do expected count? How do we do expected count?
Total times just times the probability of it.
Sample times the probability. Here's his sample. What do we have to do to figure out this number? How many do we
Just
have?
add all the
Yeah, add them all up. So 12 plus 7 plus 13 plus 4 plus 8 plus 2 gives you a total of 46 candies. So for each one, your sample size is going to be 46. For blue, it was 23. And if we look, it says blue and orange. So I'm going to put those two together. 46 times 0.23 is 10.58. Green and yellow were the same. So we would do 46 times, green and yellow was 15%, which gives us 6.9 candies. And then I'll move it up in just a second. Red and brown. 46 and 12%, which gives you 5.52. Now realize when you do part 3, where you calculate the chi-square, you have to do this one twice, and this one twice. Got it? Do it twice. So remember our formula. We're going to do our observed minus our expected. So we're going to start with blue. How many blue did you observe in the sample? 12. But we expected how many blues? 10.58. We're going to square that over that 10.58. The next one is going to kind of look the same, except we're doing orange, and it said there were only 7 oranges. So we observed 7 in the sample. We were expected to get 10.58. And then we square that over 10.58. Green. In the sample, we got 13 green. We were supposed to get 6.9 squared over 6.9. For yellow in the sample, there was 4 in the sample. Expected 6.9 over expected again, 6.9. Red, we saw 8 in the sample. We were supposed to get 5.52. Square that over 5.52. And the last one, brown, we had 2 brown in the sample. We were expected 5.52 over 5.52. When we put it in the calculator, we get 11.3724. Any questions on the check your understanding? Pretty simple. When you have homework, that's what you'll be doing. Chi-square distributions. The chi-square distributions are a family of density curves that take only non-negative values. If we think about our chi-square value, we square it so that it's not negative. Okay, so that's why the square's in there. And are skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. The chi-square test for goodness of fit uses the chi-square distribution with degrees of freedom equal to the number of categories minus 1. The number of categories minus 1. All right, so we're going to talk about those M&Ms again, but this time we're going to find the p-value. In the last example, we computed the chi-square statistic. For the random sample of 60 M&Ms, chocolate candies, milk chocolate candies, in Jerome's class, and we got that that statistic was 10.180. Now let's find the p-value. Because all the expected counts are at least 5, the chi-square statistic will be modeled well by a chi-square distribution when H sub O is true. So in our M&Ms, there are 6 color categories for M&Ms milk chocolate candies. So the degrees of freedom will be 6 categories minus 1, which equals 5. The p-value is the probability of getting a value of chi-square as large or larger than 10.180 when H sub O is true. And if you want to look in your book, the figure in your book shows this probability as an area under the chi-square density curve with 5 degrees of freedom. To find the p-value using table C, we have not looked at that. The very last table that you have. D is random digits, so C is the last one we haven't looked at, so it looks like this on T4. To find the p-value using table C, look in the degrees of freedom equals 5. I'll come back and show you this in just a second. Row. And then the value, 10.180, falls between the critical values of 9.24 and 11.07. So if we look at our book, and I'll go back to it, here's your degrees of freedom are 5, and we go across, and that's where it falls. So the 10 is between this. So it's between 0.10 and 0.05. That's the tail probability that I'm gonna talk about in just a second. Okay, so that's where that 0.10 and 0.05 comes from. All right. The corresponding areas in the right tail of the chi-square distribution with 5 degrees of freedom are 0.10 and 0.05. So the p-value for a test based on Jerome's data is between 0.05 and 0.10. All right. To find the p-value, the actual p-value on the calculator, you go to second bars. Chi-square CDF. Your lower is going to be your 10.180. Your upper is going to be a large number. And then your degrees of freedom are 5. So when you put it in there, it gives you a p-value equal to 0.07, which is between 0.05 and 0.10.
Will you always make the chi-square the lower?
Say it again. I'm sorry, I had my volume down.
Will you always make the chi-square value the lower value in that?
Because we're doing the right tail. That's why. So think about it this way,
How did you know that we were doing the right tail?
because it said it. Corresponding areas in the right tail.
Will it always be there, or will it tell us?
Yes, it will tell you, or it will just assume, but I'm pretty sure that they tell you every time. So it won't matter either way. It should be really close to that. Okay. So again, this is the right side. So your value was 10.180, and we're going to go, that's going to be your lower, and then everything's going to be upper. If they ask you for your left side, it'll be the opposite. All right. So another check your understanding. Let's continue our analysis of Joey's sample of M&M peanut chocolate candies from the previous check your understanding. Confirm that the expected counts are large enough to use a chi-square distribution. Which distribution specify the degrees of freedom should we use? So to do this, all expected counts have to be at least 5. And that's always, that's not just on the M&M problem, that is always. All right, so all of our expected counts, I'm going to flip back to show you. We had, struggling, sorry, 10.5, 6.9, and 5.52. So were all of them greater than 5? Yes, so that checks. And then which distribution specify the degrees of freedom should we use? How many different M&M flavors were there? Not flavors, but colors were there? 6. So we subtract 1 from that category to get 5. 2 says sketch a graph like figure 11.4, and you haven't done that, but I kind of sketched one just then when I did the technology corner on page 685 that shows the p-value. Right. So I'm gonna hold off on the p-value for just a minute because we haven't done the p-value. So how do we find that p-value? So back from the other one, from the previous one, our chi-square was 11.3724. So this, I don't think it's supposed to say p-value. We're gonna mark that out. I think it's supposed to say this, because that's what I have a picture of in my notes. Everything is positive. We'll start on this end at 0. This end will be 20. It doesn't matter what your scale is down there. I kind of have it backwards. It should be bigger on the end, a little more skewed. So I apologize. Why does it have to be skewed? What did they say about the distribution? It was going to be what? That's not even that great either. Remember they said it was going to be right skewed. Okay, so that's, mine is not very good. I'll try to fix it. I'm really bad at drawing curves that are skewed. Maybe that's a little better. It still kind of looks the same. And then we want to plot where 11.3724 would be. And again, as long as you make it close, it's not going to hurt anything. And then we want the right side. It says use table C to find the p-value. So I'm gonna pop that out. Remember, we're looking for 11.37 with degrees of freedom being 5. So again, here's our 5. Where does that 11.37 fall? Between what two tail probabilities? Right here, right? So it falls in between these two, so between 0.05 and 0.025. So from table C, that's what I'm going to write. From table C, p-value is between 0.05 and 0.025. Then it says use the calculator. Where do we go? Second bar. CDF. What is our chi-square value? 11.3724. Degrees of freedom are still 5. And paste. And we get 0.04. Is that between those two numbers? Yes. So then number 4 says, what conclusion would you draw about the company's claimed color distribution for M&M's, peanut chocolate candies, and justify your answer? So p-value versus alpha. So same thing we've been doing. P-value is 0.04. Alpha, because it didn't give it to us, is 0.05. What do we know? So what do we do? We'll reject H sub A. So what do we know? That what? Is it correct? Candy, color distribution. We rejected H sub O. Remember, H sub O was that the candy's claim, the company's claim was true. And then our alternate was that it was not true. So the candy color distribution is different from the company's claim. No worries. It's hard to not have all the information just right there in front of you. All right. Flip to your next one. What are your conditions for performing the goodness of fit test? Random and 10% are the same as they've always been. Large counts are different this time, and it's exactly what I just told you, the expected count. Are at least 5. Right. Suppose the conditions are met to determine whether a categorical variable has a specified distribution in the population of interest expressed as the proportion of individuals falling into each possible category. Perform a test of, here's your hypothesis, the stated distribution of the categorical variable in the population of interest is correct. Your alternate is going to be the same thing, except for it's going to be is not correct. And we just did that with the M&Ms. The company's claim was correct, or the company's claim was not correct. So remember, the way that we do that is start by finding the expected count for each of the categories, assuming that H sub O is true. Then calculate the chi-square. Remember, that's the sum of the observed minus the expected squared over the expected, where the sum is over the k different categories. The p-value is the area to the right of chi-square. So right there, Rachel, it's always going to be the right unless they justify otherwise. Under the density curve of the chi-square distribution, with k minus 1, so k standing for categories, minus 1 degrees of freedom. So now we're going to do a state plan do conclude with this. Couple more pages, we're done. Couple more pages. I do want to finish 11.1, so we're almost done. Oh, thank you so much. Appreciate that. All right. Wow. Y'all give me a minute. It's mad at me. Of course. And then I didn't have it plugged in. There we go. Sorry, my document cam quit working. Technology, yay. Okay. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game, specifically because January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if the birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table below summarizes the data on the birthdays for these 80 players. Do these data can provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? So this is a state plan do conclude. And since it's convincing evidence, we're doing hypotheses. So your null is going to be that birthdays are evenly distributed. So your alternate would be what? Or not. Make sure on your test you write it out in your notes. I don't care. Okay. What else do we need in our state? Our alpha level. And what is our alpha level on this one? Yep, 0.05 because they didn't tell us. We're doing a chi-square goodness of fit test. If all the conditions are met, our first condition is random. Was it random? Yes or no? Yes. %. What would I do? Which is 800. We want to make sure that the population is less than 800. On your final exam, I would write, assume that the population is greater than 800. Okay, just throw that out there. There are actually 879 NHL players at the time that this came out. All right. You're going to do your large counts, but what does this consist of now? Your expected have to be what? So what do we do? What would be the probability? What would be the probability?
If there's 4 categories and it was even, shouldn't it be 0.25?
You are correct. Do I have to do this 4 times?
No, you just have to make sure that all of them are above whatever.
They're all the same. You don't have to do it 4 times. Okay, so don't. Does everybody understand why it's 1/4? They were even, so the even probability means quarters, quarters, quarter, because there's 4 different categories. All right. So we're going to calculate the chi-square. How do we calculate the chi-square?
Well, we expected to have 20 for every category, so it would be 20 or 32 minus 20.
So the first one, 32 minus 20 squared over 20. The next one will be 20 minus 20 squared over 20. The next one, 16 minus 20 squared over 20. And the last one, 12 minus 20 squared over 20. This gives you 11.2. How do I find the p-value?
The chi-square CDF.
What's your lower gonna be? $11.2. Your upper? Yeah, crazy number. And then I'm gonna put it down here so you guys can see it. The last thing that you're gonna put in there, are your degrees of freedom. How many categories are there? 4 minus 1, which is 3. Okay. So I get that my p-value is 0.011. We're going to conclude. We're going to test our p-value against our alpha. Our p-value is 0.011. Alpha was 0.05. Our p-value is less than. So we reject H sub O. And what does that mean? That. Birthdays are what? Not evenly distributed. Very good. One short page and one longer page. All right. Is everybody good? Okay, chi-square test for goodness of fit on the calculator. You're going to go to stat. You're going to go to tests. And you're going to go down until you see this letter D. So I'm going to put that in front of it. And it's the chi-square GOF test. You can put your data into L1 and L2. That's your observed and your expected. You can put everything in and then have your subtraction in there at some point. But observed would be L1, expected would be L2. Degrees of freedom in this case would be, what do we have for this last one? 3. And then calculate. You can also draw, it's whatever you want to do. So when you get this, it'll give you an output. Degrees of freedom are 3. And your p-value for this one in the calculator actually gives you a more accurate 0.0106, but if we round that, it's still 0.011. Okay, so that's it if you want to do it in the calculator. But again, you have to put it in L1 and L2. L1 is observed. L2 is expected. Okay. Is everybody good, or do I need to do that in the calculator? I think you can handle it, right? So I observed would have been the numbers that they gave us in the chart. Our expected would have been what we calculated, the 80 times 1/4. All right. Same thing here. Biologists wish to make pairs of fruit flies having genetic makeup RRCC, indicating that each one has dominant gene R and one recessive gene R for eye color, along with one dominant capital C and one recessive little c gene for wing type. Each offspring will receive one gene for each of the 2 traits from each parent. The following table, known as a Punnett square, shows the possible combinations of genes received by the offspring. Any offspring receiving R gene or a capital R gene will have red eyes, and any offspring receiving a big C will have straight wings. So based on this Punnett square, the biologist predicts rations, I don't think that's right, rations of 9 red-eyed straight-winged, 3 red-eyed curly-winged, 3 white-eyed straight-winged, 1 white-eyed curly-winged. To test their hypothesis about the distribution of offspring, the biologists mate a random sample of pairs of fruit flies. Of 200 offspring, 99 had red eyes and straight wings, blah, blah, blah. Do these data differ from what the biologists had predicted? Carry out the test at the alpha equals 0.01 significance level. So we're going to do our state plan, do conclude.
Will there be a lot of them this wordy?
Possibly. All right, what's your null hypothesis? Read it right here. Do these data differ from what the biologists have predicted? So what is your null? What the biologists predicted. What's your alternative?
What would we like need to fully put for that besides just the biologist predicted?
You can just say the percentages that the biologists have predicted or the results that the biologists predicted. It doesn't have to be crazy.
Okay, thanks.
What's your alternative? You can just say not predicted. Not what the bio predicted. What's our alpha level in this one? 0.01. We're going to do a chi-square goodness of fit test if conditions are met. What are our conditions? Random. Is it random? Yes. 10%.
There's probably more flies.
Probably way more than 2,000 in a population of fruit flies. I feel like that happens in the summertime in my house. Ugh. So annoying. All right, last one. And what do we have to do here? What do you mean? What's your percentage? What's your percentage? Let's even start. We're going to start with red eyes. Red eyes. There were 200 offspring, so that's your sample size, right? What was our percentage predicted of red eyes? So that's not this paragraph. That's this paragraph. So we had 9 out of 9, 10, 11, 12, 13, 14, 15, 16. Everybody see that? And I left it in not the decimal, I left it in the fraction so that you can remember the total is 16. This actually gives you 112.5, so that's greater than 5. Then we have red eyes and curly wings. So red eyes and curly wings was 3 out of 16. So 200, 3 out of 16 is 37.5. We had white-eyed curly wings, 1 out of 16. Gives you 12.5. And then our last offspring. Oh, did I screw that up? I did. This should have been white and curly, white and straight was 3 out of 16. Doesn't matter what order I put it in. I should have 2 3 out of 16s. I didn't have to do that one a second time. I think that's why I skipped over it anyway. All right, so are they all greater than 5? Yes. Our do, we're going to find our chi-square. We do our observed minus our predicted. Our observed was 99. Our predicted was 112.5. Are y'all okay if I don't write the formula down? All right, so that gives you a value of 6.1867. What are our degrees of freedom? 4 minus 1 categories is 3. How do we figure out our p-value? Where's it at? Up or lower degrees of freedom, 3. You want to copy all that down? I did 6.1867. Make sure that you justify what that is, lower, upper degrees of freedom. And I got 0.103. Then we conclude. And what do we conclude? Our p-value of 0.103 is what? Compared to our alpha? Greater than. So we. Which means? We don't have convincing evidence. The data differs from what the biologists have predicted. Yep. Any questions? That's all of 11.1. Is everybody good? All right. Because everybody was here, I'm not going to give you any homework. I'll set your homework for tomorrow's work. Got it? So everybody's good to go in here. I already have all of you for attendance. I'm going to stop share, stop recording.